Welcome back, meteorology students. This is the first lecture of two lectures for week 4. This week we'll be learning humidity, condensation, and clouds. So this specific lecture is on circulation of water in the atmosphere, or the water cycle, evaporation, condensation, and saturation, measures of humidity, and then also the heat index. Okay, so you might have some ideas of what the water cycle is in your head. You might know what it is. We all pretty much do understand, since it's a cycle, there's going to be something, of a cycle to it, I guess. There's going to be water added and then water removed. And there's going to be some sort of cycle to this. It could be added and then removed. Now, it doesn't exactly happen like either one of these, but I thought it was cute, so I included it in my lecture. And this is going to be what the actual water cycle is. We have it beginning with precipitation. This is going to be some sort of precipitation, regardless of what form it's in. It's going to come down onto the earth. It's going to run into groundwater. It's going to go into lakes and streams and glaciers. It's going to run off into the ocean. And then evaporation is going to take place. Evaporation off the oceans, off the lakes, off the glaciers. We'll also have transpiration, which is basically evaporation off of plants. So it's going to evaporate and turn into water vapor into the air. At some point, that water vapor will condense into water droplets, and that will form a cloud. Now, this cloud might be transported over land, still over water. It's going to move, though, where it's from to somewhere else due to the winds. And then it's going to precipitate the liquid out of, not the liquid necessarily, but the water, whatever form it may be in, out of the cloud, and then this whole process starts again. So the main parts of the water cycle are going to be precipitation, evaporation, and then condensation. And this cycle just repeatedly goes over and over and over again, which is great because it's our natural way, the Earth's natural way of handling water and cleaning the water and doing all sorts of different things. Now, like I said, it has evaporation, which is where it turns from a liquid into a gas, condensation, where the gas changes into the liquid, and then precipitation. And that's why I was super careful not to say rain specifically, because it can be any liquid or solid water that falls from the atmosphere. So any type of phase that it might be in. So it could be in rain or snow or sleet or hail or graupel. We don't get very much snow, sleet, or hail here in the Bay, but other areas in Nebraska, I know it's snowing a lot. So, just think all over the world, depending on how it might fall. All right, so saturation, we like to describe this as if there's some water inside of a jar or a container. And so we have the liquid, and it has a certain temperature to it, so these molecules will be moving around. All right, some of these molecules will go from the water into the air right above it in the jar, and that process would be evaporation. Some of them will be going from the air down into the liquid. That process would be condensation. Now, if the number of molecules that are evaporating are greater than condensing, then we have net evaporation. If the number of molecules that are condensing is greater than the ones evaporating, then we have net condensation. It's just kind of like a math equation. If one number is going to be larger than the other, then that means that variable has more associated to it, whatever we're talking about. All right, but what if we put a lid on top of this jar, and this prevents any of the air from escaping? Eventually, the amount of evaporation and condensation would become equal, right? There'd be no more of these molecules. They wouldn't be exchanged between the air above it and the water below it. That means that the air is saturated. It has as much water vapor it can potentially hold. That means that the relative humidity is 100%. So that also means that the amount leaving is equal the ones coming into the liquid. So there isn't any net evaporation or net condensation. It's just equal. Now, like we said, evaporation is water changing from a liquid to a gas. is there's two things that can happen to enhance evaporation. One is we can increase the liquid temperature. If we did that, then these molecules are going to move around faster, and more of them would actually go from the liquid into the air above it. Another way would be to enhance the wind speed. If we enhance the wind speed, then it'll move whatever air there is right above the water to another area, and new air will come in, and there'll actually be a new requirement for saturation. This is exactly how blow drying your hair works, right? So you're gonna take the blow dryer, it's gonna go onto your hair, and it's gonna immediately, that like layer of air right around your hair is gonna become saturated and move it away, and then new air will come in. So the next piece of the water cycle would be condensation. So this is the process where water vapor changes into a cloud droplet. So remember, water vapor is invisible. You can't see it. It's when it condenses into a, liquid form, into a water droplet, that's when we begin to see it as a cloud. But for condensation to happen, it actually has to have something to condense upon. And this something was called a cloud condensation nuclei. Now, a CCN, or cloud condensation nuclei, can be something like dust or sea salt or smoke. Any small little particle inside the air can act as a cloud condensation nuclei. Now, if enough of molecules stick to the nuclei, then it can become large enough to form a droplet. And condensation occurs usually as temperature cools. We'll go over that here in a minute with dew point. Okay, so here's going to be kind of a size comparison. Right here, this is going to be what a cloud condensation nuclei is. They're very, very small little little itty bitty molecules of something. And you can see that water would condense upon it and turn into moisture droplets. And this is going to be like a cloud right here. But eventually enough of these will actually come together and form a raindrop. Now you can see in this raindrop, first of all, it's huge compared to the cloud droplet or the moisture droplet. And the other thing is that it has many, many, many different cloud condensation nuclei in it. So you'd have to combine a lot of these in order to come up with one raindrop. Now here's the group questions. As usual, please just pause the video, see if you can answer these yourself. Right now I'm going to move along though. Okay, so humidity. Humidity is going to be the index to describe the amount of water vapor in the air. There's actually a couple different types. We have absolute humidity, specific humidity, and mixing ratio, and then relative humidity. Now, meteorology students need to know all four of these, but I don't think I have any meteorology students in my class, maybe one or two, but for the rest of you guys, it's okay just to know relative humidity. I want you guys to be exposed to the fact that there's a few different ways to actually measure humidity and the amount of water vapor in the air. And we actually use different ones for different equations and to look at different values in different ways. So, but right now we're just going to go over relative humidity. The ratio of water vapor in the air to the amount that can hold at that temperature and pressure. So the relative humidity is the ratio of water vapor in the air to the amount that can be held at that temperature and pressure. So each temperature and pressure has an amount of water vapor that can be held inside the air, and the relative humidity is basically a percentage of how much vapor is in the air to how much is there actually able to be inside the air. Now, it also can say how close the air is to being saturated. So like I said, it's expressed as a percentage. So if there's a relative humidity of 50%, that means that the air is holding half of the water vapor it can possibly hold. If it's 25%, then it's holding a quarter of the amount of water vapor that it could potentially hold. Now, there's two ways to actually change relative humidity. The first way is to increase or decrease the amount of water vapor in the air. And the second one is to increase or decrease the temperature. This actually happens, daily with our changing temperature between day and night. So as you see here, this is going to be the temperature right here, or relative humidity, like increasing or decreasing, and then the time of day down here on the x-axis. So you can see at midnight, our temperature is getting colder and colder and colder until 6 a.m., which last week we talked about how that's the coldest time of the day. So as the temperature is getting colder and colder, the relative humidity is actually increasing until we get to the coldest part of the day and it turns around and the temperature starts getting warmer. At that point, the relative humidity starts decreasing until we get to the warmest part of the day, which we've also learned last week was around 4 o'clock in the afternoon. And at that point, it turns around again and starts decreasing. That is where the relative humidity starts increasing. So there's an inverse relationship between the relative humidity and the temperature. As the temperature decreases, the relative humidity increases. And the opposite, if the temperature is increasing, then the relative humidity decreases. All right, so like we said, there's going to be two different ways that you can change the relative humidity. The first one is, going to be like up here we have where we're adding more water vapor into the air. Just by simply doing that, that's going to increase the relative humidity. And this down here might be covered up by my picture here, but one of them is showing you how if you change the temperature, that the molecules are going to move around a lot faster. And so that's actually going to decrease the relative humidity. There's going to be more places in between those water molecules where we can actually add more water vapor. So the second way of looking at how much moisture is in the air is by looking at the dew point temperature. Now, the dew point temperature represents the temperature the air would have to be cooled for saturation to occur. So notice it said cooled. So the dew point temperature is usually cooler than the outside temperature. The indicator of this is actually a very good indicator of the air's actual water vapor content. So when the air temperature and the dew point are close together, the relative humidity is high. And when the air temperature and dew point are far apart, that means that the relative humidity is low. Like I said, the temperature is going to be below the relative humidity, going up to potentially the same. It's not going to be above it. So, if we have like the outside temperature of 80 degrees and a relative humidity of 50 degrees, that's going to be pretty far apart. That's 30 degrees apart. So it's not going to be very high relative humidity. But if we have an outside temperature of 80 degrees and a dew point of 80 degrees, then the relative humidity is going to be 100%. That air is going to be saturated. So we can actually look, and dew point is measured by our balloons, our balloons that we put up into the atmosphere, our weather balloons. And so we can actually see how close to saturation the air is just by looking at the outside air temperature and the dew point temperature. And this is a good example of that. So which one has the highest relative humidity? The polar air, where the temperature is going to be, the outside air temperature is going to be 28 degrees Fahrenheit, and the dew point will be 28 degrees Fahrenheit. Or the desert, where the air temperature would be 95 degrees Fahrenheit, and the dew point is going to be 41 degrees Fahrenheit. So I'd like you to try and figure that out. Pause the video, think about it. But the answer is actually going to be the polar air. That, we know that because you can see that the air temperature is going to be equal to the dew point temperature. These two are exactly the same. That means that the air is actually saturated right here and that the relative humidity is 100%. But the air temperature is 95 over here where the dew point's 41. Those two numbers are really far apart, which means to us that it's not very close to saturation. So it's pretty dry air, which would make sense in the desert. Okay, this is going to be dew points in January versus July. You can see in January, the dew points are going to be like 40 degrees over here where we live. It'd be more like 10 degrees, over here. What is it? The middle United States. Here's Omaha. So usually and on average, it would be, 20 degrees dew point. Where on the flip side, in July, same place in Omaha, you're going to find, generally speaking, in the 60 degrees, 70 degrees over here in the southern United States. Over here where we live, it'll be more like 50 degrees. Kind of cool how it does that little swoopy thing, right? Okay, so what that means is, and during the summer, the outside temperature is going to be like 90, 95 degrees in Florida, in the south. So there's going to be a good 20-degree difference between the outside air temperature and the dew point. Over here, we're going to see 50 degrees. It could potentially get to be 50 degrees in January in this area of Florida. I was there a couple of years ago, and it's colder than you think, I think, in Florida during the winter. You always think about it being sunny and warm, but it's not. So, it's easier for relative humidity or saturation to be achieved when the air temperature outside is cooler. Because remember, the dew point is going to be colder than the air temperature usually, unless they get closer together, in which case you're getting closer to saturation. But how hot does it feel? What does this whole dew point and humidity, business have to do with how we feel? So if you look, it's going to be very similar to the wind chill factor, where we have the air temperature on the y-axis and the dew point temperature on the x-axis. We're just going to do the same type of thing that we did before. If we look at like 95-degree air temperature, I don't know, and 75-degree dew point, you can see that it's going to feel like it's 107 outside, and it's in this orange color, which is in danger. It feels, pretty warm out. You're in danger of sunstroke, muscle cramps, heat exhaustion, heat stroke. So people like the elderly, people that, trying to think, babies that have a problem with being exposed to extreme temperatures, or people that work outside, they're at real risk of having sunstroke or anything like that with the air temperature, or with the dew point. I'm sorry, with the heat index. So basically, what I'm trying to say is the dew point has a lot to do with how we feel and how we get too warm. So over here, we can see that 66 to 70%, we're going to feel uncomfortable. Not 70%, I'm sorry, this is the dew point, so the temperature. So 61 to 65 degrees, it'd be sticky. 66 to 70 to be uncomfortable. In Nebraska, it gets really hot and humid during the summer. And so when you go from the air conditioning to outside, it's kind of like hitting a brick wall. It's hard to breathe. Being in the shade doesn't matter. Here, it's kind of interesting to me because you can go in the shade and it's actually cooler than it is if you're in the sun. It's different than that when you're in a humid climate, because it doesn't matter if you're in the shade or not. It's just hot and you're uncomfortable and you're sweating and it's just hard to breathe because the air is really heavy. It has so much water vapor in it. So, and it feels warmer than it actually is outside. So, dew point has a lot to do with our comfortability and how we feel, and our if we're exposed to high temperatures, if we're likely to get heat stroke or not. That's why a lot of air conditioners, they take the water vapor out of the air. They literally just suck it out. It dries the air out, and that's so that we can feel more comfortable. And this is going to be the group questions for this lecture. So I will see you guys in part 2. Thanks.